So let's start. First, we need to understand what machine learning means with a use case or with an example. We need to know the different types of machine learning and also how machine learning can be used in different industries in the world. For this, you can check out the Intro to ML video by the Programming Knowledge channel and also read multiple blogs online which explain ML better. The next thing is Python programming skills. As we all know, Python is the widely used programming language for machine learning. So we must have the Python program basics right to start learning machine learning. Again, the Programming Knowledge channel has Python tutorial videos which you can check out to get your basics right. And you can also follow different tutorials and blog posts online. The next thing is basic mathematical skills. Machine learning has a lot of mathematics involved behind the scenes, and to understand machine learning properly, one must have these basics in their bags. First is linear algebra basics. We should know how to solve a linear equation in one variable or two variables. And for probability basics, we just need to know the very simple basics of probability, the basic formula and how probability works. After this, we can branch out to do different types based on what our end goal is. So the first is academic machine learning. If you want to produce novel research, write research papers, read research papers, build machine learning tools from scratch, and understand the deep underlying concepts, then you can refer to these prerequisites before jumping into the academic machine learning part of it. So let's start. The first thing is strong mathematical concepts. As you'll be producing novel research, new research, or try to read complicated research papers and also build tools from scratch, you should have a strong mathematical foundation. In algebra, we must know how logarithms work, how matrices work, how to perform matrix multiplication, and things like that. In calculus, we should know what is the concept of a derivative, what is the chain rule, partial derivatives, and gradients. In statistics, we should know the simple statistics basics, which is mean, median, mode, then how outliers work, the ability to read an histogram, and some algorithms like conditional probability. Next is intermediate Python programming. Since we'll be writing some tools from scratch and also write the code for the new type of algorithms which we read or try to implement, we should have some intermediate Python programming skills and use some complicated structures which can help us write better code. For this, we can learn list comprehensions, lambda functions, and also learn some third-party libraries which make our jobs easier. And the last thing is strong programming science, computer science fundamentals. As a computer science graduate, or not being one, we should have some simple data structures and algorithms in our bag just to make sure that the concepts which we implement are being implemented in the most efficient way possible. This is academic machine learning. This helps you get into the academia faster and also will help you have a better learning curve than before. The next is industrial machine learning. Now, if you want to work in an industry or in a company or be a software engineer with a machine learning specialization, if you want to create new products, business value, and apply existing off-the-shelf tools to solve business problems, then you can refer to this as the prerequisite. So, in a company or being a software developer with a machine learning specialization, the first thing which you need to know is intermediate or advanced Python programming. So, as you'll be writing a lot of code and you'll be busy focusing more on writing code than doing research, the companies will expect you to know a lot of Python to use the tools which are off the shelf. Again, things like list comprehension, lambda functions, and also understanding how third-party libraries work with machine learning. The second thing is similar to the academic machine learning part of it, which is strong computer science fundamentals, because these fundamentals will be useful no matter which branch you are in. And next we come to the most important part, data analysis. So before trying to implement machine learning algorithms in a company, one must need to know what the data is, what the data is trying to represent, and also understand how the data works. So people should have a proficiency with frameworks and tools such as pandas, matplotlib, and seaborn. In the upcoming videos, we'll talk about how these frameworks work and also look at them with the code. Lastly, people who would like to work in a company as a software engineer or as a data scientist, they should have minimum Linux skills. They should know how to work on the terminal, how to work on the command line, how to use that to their benefit, and also make sure that they have enough to write most of the simple code on the terminal. Now, these are some prerequisites which I feel can give you a better learning curve when you're trying to jump into machine learning. You can also explore both the branches. You can try academic machine learning first and you can jump onto industrial or vice versa. Now, let's talk about some resources. All the resources to learn these prerequisites will be in the description below, and also this Notion document which you see here will also be in the description below. If you have any questions, please use the comment section below to ask them. In this video, we'll start with what is linear regression, the intuition behind the algorithm, and understanding all the elements of it. Let's have an overview of linear regression. It is one of the most basic machine learning algorithms and easy to implement. The algorithm has already been used in statistics and is a common process used in many applications of statistics in the real world. So, what is linear regression? By definition, it is used for finding a linear relationship between the target and one or more predictors. The idea behind linear regression is to fit the observations of two variables into a linear relationship between them. In simple terms, the task is to draw the line that is best fitting or closest to the points where the x-y coordinates are observations of the two variables which are expected to depend linearly on each other. In more simpler terms, given two variables x and y, the model can predict values of y given future observations of x. This idea is used to predict variables in countless situations. Example, the outcome of political elections, or the behavior of the stock market, or the performance of a professional athlete. There are two types of linear regression, simple and multiple. In this video, we'll only cover simple linear regression. So, we had talked about drawing a line that is closest to the points which are our variables. This line can be modeled based on a linear equation shown on the slide. Here, x and y are our variables which will be present in the dataset. The motive of the linear regression algorithm is to find the best values for a0 and a1, which we call the parameters. Before moving on to the algorithm, let's have a look at two important concepts you must know before understanding linear regression. The cost function. The cost function helps us to figure out the best possible values for a0 and a1, which would provide the best fit line for the data points. The difference between the predicted values and the ground truth measures the error difference. We square the error difference and sum over all the data points and divide that value by the total number of data points. This provides the average squared error over all the data points. Therefore, this cost function is also known as the mean square error. By cost, I mean the cost of incorrectly predicting a data point or how far the line is from the point. Mathematically, we find the mean distance between all the points and we want to minimize that distance so that the line fits the data perfectly. To minimize the cost function, we use a technique called gradient descent. The next important concept needed to know linear regression is gradient descent. Gradient descent is a method of updating a0 and a1 to reduce the cost function. The idea is that we start with some values of a0 and a1 and then we change these values iteratively to reduce the cost. Gradient descent helps us how to change the values. To update a0 and a1, we take gradients from the cost function. To find these gradients, we take partial derivatives with respect to a0 and a1. Now to understand how partial derivatives work, you would require some calculus, but if you don't, it is alright. You can take it as it is. The partial derivatives are the gradients and they are used to update the values of a0 and a1. Alpha is the learning rate here, which is a hyperparameter that you must specify. A small learning rate could get you closer to the minima, but takes more time to reach the minima. A larger learning rate converges sooner, but there is a chance that you could overshoot the minima. This can be depicted on the slide. To implement the algorithm, we have two choices. We can use the scikit-learn library to import the linear regression model and use it directly, or we can write our own regression-based model based on the equations above. In this video, we'll implement linear regression using the scikit-learn library. To learn more about what is linear regression, you can check out the link to the video in the description. The entire code and the dataset can be downloaded using the link in the description, which will direct you to this GitHub page. After this, download the data directory and store that in your projects folder. Let's start with the implementation. I'm using a Jupyter notebook here, but you can implement the same in a single Python file as well. First, we start with importing all the libraries and the dependencies that are required. We need the pandas library to manipulate the dataset. Next, we import the matplotlib library to visualize our data and the results. We use the pyplot here. And lastly, we need the linear regression model from the scikit-learn library, which is the main dependency. So from sklearn dot linear model, we import the linear regression class. Now we start with reading our data into the code using pandas. Make sure that the data directory is in the projects folder. We use the read CSV function here because our data is in the CSV format. We move inside a data directory and use the advertising dataset. Let's just check if the spelling is right. And yes, that should be good. Now, to see what the data looks like, we use the head function, which is data.head. As you can see here, the column unnamed 0 is redundant and hence we need to remove it. To remove a column, we can use a drop function in pandas. We have to remove the unnamed column, unnamed 0, and we specify the axis equal to 1. Here, axis is equal to 1 to remove the entire column, and the axis is equal to 0 to remove only an index. As you can see in the output, the unnamed 0 column has been removed. Alright, now our data is clean and it is ready for linear regression. For simple linear regression, let's consider only the effect of TV ads on sales. Before jumping right into the modeling, let's look at what the data looks like. We use matplotlib, a popular Python plotting library, to make a scatter plot. Let us set a size of the plot, which can be 16,8. Then we generate a scatter plot using the scatter function, in which we have the TV ads and the sales. Let's color the scatter plot with a black dots. And as you can see, there is a clear relationship between the amount spent on TV ads and the sales. Let's see how we can generate a linear approximation of this data. First, we convert these values into vectors and then store them into two variables. So x is equal to data of the TV ads, their values, and we convert them into vectors using the reshape function, which is -1 and 1. Then we do the same for the sales, which is data of sales and their values, which are converted into vectors. Now after this, we use the fit function of the linear regression class to fit a line on the x and y values. Let's name the variable reg, which is linear regression object, and then we call the fit function on x and y. The minimization of the cost function using gradient descent works behind the scenes here, behind the fit function. To learn more about the cost function and how gradient descent works, you can check out the introduction to linear regression video in the description below. Now, we have fit a straight line to the data set, and let's visualize this using a scatter plot again. Now, since the code for visualizing the best fit line is long, I'm going to copy paste it, but the entire code will be available in the GitHub repo. Now here, first we predict all the values on the X data set, and then we use those predictions to make a line on the scatter plot. Here, the dots will be in black and the line will be in blue. The X label will be the money spent on the TV ads, and the Y label will be the sales. From the graph, it seems that a simple linear regression model can explain the general impact of amount spent on TV ads and sales. This is how we implement linear regression in scikit-learn using the scikit-learn library. Okay, we'll talk about what is logistic regression. Classification techniques are an essential part of machine learning and data mining applications. Approximately 70% of problems in data science are classification problems. There are a lot of classification problems that are available, but the logistic regression is common and is a useful regression method for solving the binary classification problem. Logistic regression can be used for various classification problems such as spam detection, diabetes prediction, if a customer will purchase a product or not, whether the user will click on a given ad link or not. Logistic regression is one of the most simple and commonly used machine learning algorithm for two-class classification. It is a statistical method to predict binary classes. Its basic fundamental concepts are also used in deep learning. It is a special case of linear regression where the target variable is categorical in nature. It uses a log of odds as a dependent variable. Logistic regression predicts the probability of a binary event utilizing a logic function. As we can see here, we need to categorize the data in two different categories, and our job is to define the line which does that. Now, why is it called logistic regression if it's a classification mechanism? Contrary to popular belief, logistic regression is a regression model. The model builds a regression model to predict the probability that a given data entry belongs to the category numbered as 1. Just like linear regression assumes that the data follows a linear function. Logistic regression models the data using the sigmoid function. Linear regression gives you a continuous output, but logistic regression provides a constant output. An example of continuous output would be house price prediction or stock price prediction. An example of discrete output is predicting whether a patient has cancer or not, or predicting whether a customer will click on an ad or not. Now, let's modify the linear regression equation we had seen in the previous video for logistic regression. We apply something called as a sigmoid function on the linear regression equation. Let's see what the sigmoid function is. The sigmoid function, also called the logistic function, gives an S-shaped curve that can take any real valued number and map it into a value between 0 and 1. If the curve goes to positive infinity, y predicted will be 1, and if the curve goes to negative infinity, y predicted will become 0. If the output of the sigmoid function is more than 0.5, we can classify the outcome as yes or a 1. And if it is less than 0.5, we can classify it as 0 or a no. For example, if the output is 0.75, we can say in terms of probability as there is 75% chance that patient will suffer from cancer. Just like we have a cost function in linear regression, we need one for logistic regression as well, which has to be reduced to obtain the best fit line. But the cost function used in linear regression will not work here. If you try to use the linear regression cost function in a logistic regression problem, you would end up with a non-convex function, a weirdly shaped graph with no easy way to find minimum global point. Hence, we have a different cost function for linear regression. For logistic regression, the cost function is defined as minus log h of x if y equal to 1 and minus log 1 minus h of x if y equal to 0. This is the cost the algorithm pays if it predicts a value h theta of x while the actual cost label turns out to be y. By using this function, we will grant the convexity to the function the gradient descent algorithm has to process. There is also a mathematical proof of how we get this cost function, which is outside the scope of this video. The final cost function can be seen at the bottom of the slide. Now, we have the hypothesis function and the cost function, and we are almost done. It is now time to find the best values for our parameters in the cost function, or in other words, to minimize the cost function by running the gradient descent algorithm. The procedure is identical to what we did for linear regression. To understand more about gradient descent, please find the link in the description which will explain linear regression and also gradient descent. To minimize the cost function, we have to run the gradient descent function on each parameter, and that is how logistic regression works. At the end, we get the best parameters that can work with the hypothesis function to predict whether a data point belongs to one class or the other. Now, for the implementation, we can either use the scikit-learn library to import the logistic regression model and use it directly, or we can also write our own model based on the equations above. Logistic regression is amongst the most commonly known core machine learning algorithm out there, with its cousin linear regression. It has many applications in businesses, one of which is the pricing optimization. In this video, we will learn how to code logistic regression in Python using the scikit-learn library to solve a bit pricing problem. Let's have some recap. Logistic regression is a predictive linear model that aims to explain the relationship between a dependent binary variable and one or more independent variables. The output of logistic regression is a number between 0 and 1, which you can think of as being the probability that a given class is true or not. The output is between 0 and 1 because the output is transformed by a function which is usually the sigmoid function. Let's start implementing logistic regression in Python with a very simple example. Note that the intent of this video is only to implement a very basic logistic regression model using scikit-learn without using a train test split on the dataset and with minimum data visualization. So let's start. First, we import all the dependencies that are required. We need matplotlib for visualization, so we need the pyplot as plt. Next is numpy to store our data, and finally we need the sklearn logistic regression model, which we can use to fit our data. Yeah. So the next is that we have to define a dataset. Let's generate a dataset that we will be using to learn how to apply logistic regression to a pricing problem. The bid price is contained in our x variable, while the result, a binary lost or 1 category, is encoded as 1 or 0 in our y variable. Here I have defined my own dataset, but for complicated or more advanced examples, you can also import a dataset from Kaggle and use that. Let's go ahead and visualize this data using matplotlib to gain a better understanding of what we're dealing with. Let's have a scatter plot of x and y, and let's actually give it a title of pricing bids, and the x label is going to be price and the y label is the binary output, won or lost. So status 1 is a won and 0 is a lost. So here each point above represents a bid that we participated in. On the x-axis you can see the price that was offered, and on the y-axis you see the result if we won the bid or not. Our goal is to use logistic regression to come up with a model that generates the probability of winning or losing a bid at a particular price. In Python, Logistic regression is made simple thanks to the scikit-learn module. For the task at hand, we'll be using the logistic regression class by the sklearn linear model. So log reg, let that be the name of the variable, and logistic regression class, where the regularization strength C is equal to 1.0, and the solver, let that be LBFGS, which is an optimization just like it in Descent. And for multi-class, we specify OVR because we're using a binary classification problem here. So multi-class is equal to OVR for binary classification. The next step is to fit the logistic regression model by running the fit function of our class. And before we do that, we transform our X array into a 2D array as is required by the sklearn model. This is because we only have one feature, which is the price, and if we had more than one feature, our array would already be 2D. So let's reshape our data as 1 comma minus 1 comma 1, and finally we can fit our model. So log reg dot fit capital X and Y. Now we have a model, and now let's predict some data. If we wanted to run the prediction on a specific price, you can also do that as shown. So let's print a prediction. Let's say we need to find whether we've lost or won if the price is 110. So as you can see on the graph above, if the price is 110, we should be winning. So let's try that. And as you can see, when the price is around 110, which is between 100 to 200, we win the bid. And if the price is around 275, we should lose the bet. So let's try that again. With 275, we should lose the bet. And as you can see, we have lost the bet. This is a very basic implementation of logistic regression using the scikit-learn library to understand how the algorithm works on a dataset. As we have a basic understanding now, we can start working with the Kaggle dataset and also study more about data analytics and data visualization. This video is an introduction to support vector machines. For an in-depth understanding, please refer to the links in the description. Support vector machines are perhaps one of the most popular and talked about machine learning algorithms. They were extremely popular around the time they were developed in the 1990s and continue to be the go-to method for a high-performing algorithm with a little tuning. Support vector machine is a supervised machine learning algorithm which can be used for classification challenges. In addition to performing linear classification, SVMs can efficiently perform on non-linear classification as well. So, what are support vector machines? It is a discriminative classifier formally defined by a separating hyperplane. In other words, given labeled training data, the algorithm outputs an optimal hyperplane which categorizes new examples. In simple terms, an SVM model is a representation of the examples as points in space mapped so that the examples of the separate categories are divided by a clear gap that is as wide as possible. Let's visualize this. In this graph, we can see that the two classes are separated by the largest gap possible. The space between the red line and the closest point to the red line is called a margin. So, for one-dimensional data, the support vector classifier is a point. For two-dimensional data, the support vector classifier is a line as seen in the previous slide. For three-dimensional data, the support vector is a plane. And for four-dimensional or more, the support vector classifier is a hyperplane. So, let's talk about the hyperplane now. A hyperplane in an n-dimensional Euclidean space is a flat n-1 dimensional subset of that space that divides the space into two disconnected parts. So, a line is a hyperplane, or even a 2D plane for a 3D data is a hyperplane. SVM algorithms use a set of mathematical functions that are defined as the kernel. Sometimes it is not possible to find a hyperplane or a linear decision boundary for some classification problems. If we project the data into a higher dimension from the original space, we may get a hyperplane in the projected dimension that helps to classify the data. Let's see what we mean here. As shown in the figure, it is impossible to find a line to separate the two classes green and blue in the input space. But after projecting the data into higher dimension, we were able to classify the data using a hyperplane. Hence, kernel helps to find a hyperplane in the higher dimension space without increasing the computational cost much. Usually, the computational cost will increase if the dimension of the data increases. The mathematics behind how kernels work is out of scope for this video. The SVM model needs to be solved using an optimization procedure. You can use a numerical optimization procedure to search for the coefficients of the hyperplane. The most popular method for fitting an SVM is the sequential minimal optimization (SMO) method that is very efficient. It breaks the problem into subproblems that can be solved analytically by calculating rather than numerically by searching or optimizing. In the next video, we'll implement the support vector machine. We have two choices here. We can either use the scikit-learn library to import the SVM model and use it directly, or we can write our own model based on the equations above. A support vector machine is a type of supervised machine learning classification algorithm. SVMs were introduced initially in the 1960s and were later refined in 1990s. However, it is only now that they are becoming extremely popular, owing to their ability to achieve brilliant results. SVMs are implemented in a unique way when compared to other machine learning algorithms. In this video, we'll implement support vector machines with the help of the scikit-learn library. For the implementation, our task is to predict whether a bank currency note is authentic or not based on four attributes of the note. Those attributes are the skewness of the wavelet performed image, the variance of the image, entropy of the image, and the kurtosis of the image. This is a binary classification problem, and we will use the SVM algorithm to solve this problem. The detailed information about the data and a link to download the dataset can be found in the description. Download the dataset and store it locally on your computer where you intend to write the implementation. So let's start the implementation by importing all the necessary libraries. First, we need to import pandas as we need to store our data in a data frame. And the next is NumPy, followed by matplotlib, and then we need the scikit-learn modules. Here we'll be using the train test split module, which we have had not in the previous videos for linear and logistic regression implementations. But for SVM, we'll actually have a train test split and see how the algorithm works on the test data. Next, we need to import the SVM class, which is SVC, support vector classifier. And at last, we need to evaluate our algorithm. So we'll need some metrics for that. And let's use the classification report module. And yeah, I think we're done. So now let's import the data. Okay, I think we have some problem. Yeah, it's a spelling mistake. Dot metrics. I have a lot of spelling mistakes here. Okay. Now let's import the data into our program. To read the data from the CSV file, the simplest way is to use the read CSV method of the pandas library. The following code which I'm going to write is going to read the bank currency note data into a pandas data frame. Let's have bank data equal to pd dot read csv, and the name of the CSV file is bill authentication, which you can find in the description of the video. Okay, now there are virtually limitless ways to analyze datasets with a variety of Python libraries. For the sake of simplicity, we will only check the dimensions of the data and see the first few rows. To see the rows and columns of the data, execute the following command. And in the output, you'll see 1372,5. This means that the banknote dataset has 1372 rows and 5 columns. Now, to get a feel of how our dataset actually looks, let's actually see the first 5 rows of the dataset using the head command. And here you can see the first 5 rows of dataset, and you can also see the attributes of the dataset are numeric. The label is also numeric, that is class 1 or 0. Let's pre-process the data before training the model. Data preprocessing involves two steps. First, dividing the data into attributes and labels, and second, dividing the data into training and testing sets. To divide the data into attributes and labels, execute the following code. Let x equal to the attributes, so bank data dot drop 1, and y equal to bank data class, which is the label. In the first line of the script in the cell, all the columns of the bank data frame are being stored in X except the class column, which is the label column. The drop method drops this column. In the second line, only the class column is being stored in the Y variable. At this point of time, X variable contains attributes while the Y variable contains corresponding labels. Once the dataset is divided into attributes and labels, the final pre-processing step is to divide the data into training and test sets. Luckily, the model selection library of the scikit-learn library contains the train test split method that allows us to seamlessly divide the data into training and test sets. Let's write the code for that. Xtrain, comma, xtest, comma, ytrain, comma, ytest is equal to train test split x comma y, and we want the test size to be 20%. Yeah, we have divided the data into training and testing sets. Now is the time to train our SVM on the training data. Scikit-learn contains the SVM library, which contains built-in classes for different SVM algorithms. Since we are going to perform a classification task, we will use the support vector classifier class, which is written as svc in the scikit-learn's SVM library. This class takes one parameter, which is the kernel type. This is very important. In the case of a simple SVM, we simply set this parameter as linear, since simple SVMs can only classify linearly separable data. Let's write the code for that. So svc classifier is equal to svc, and the kernel is equal to linear. The fit method of the svc class is called to train the algorithm on the training data, which is passed as a parameter to fit the fit method. svc classifier dot fit xtrain, comma, ytrain. To make predictions, the predict method of the svc class is used. So y prediction is equal to sv classifier dot predict x test, and let's actually print ypred to see our predictions. And as you can see, the algorithm has been run on the X test data, and all the predictions have been saved in the ypred variable, and we can see the predictions for each of the row for X text. Now, to evaluate the algorithm, confusion matrix, precision, recall, and F1 measures are the most commonly used metrics. Scikit-learn's metrics library contains a classification report which can be readily used to find out the values for these important metrics. So let's actually print the classification report for y test and y pred. So here, as you can see, the most important metric which we can see is the output of the accuracy of our algorithm, which is 99%. This is a very basic implementation of SVM using the scikit-learn library, and now you can go ahead and implement the algorithm on different datasets from Kaggle, etc. This video is an introduction to random forest. For in-depth understanding, please refer to the links in the description. A big part of machine learning is classification. That is, we want to know what class an observation belongs to. The ability to precisely classify observations is extremely valuable for various business applications, like predicting whether a particular user will buy a product or not, or whether a loan has to be given to a person or not. In this video, we'll talk about the random forest classifier. Random forest is a flexible, easy to use machine learning algorithm that produces, even without hyperparameter tuning, a great result most of the time. It is also one of the most used algorithms because of its simplicity and diversity. It can be used for both classification and regression. So, before learning about random forest, one must know how decision trees work. So, make sure that you know what are decision trees before watching this video. You can find a very good explanation of decision trees in the link in the description. So, let's start. What are random forests? Random forest is a supervised learning algorithm. The forest it builds is an ensemble or a group of decision trees, usually trained with the bagging method. We'll talk about bagging a little late in the video. The general idea of bagging method is that a combination of learning models increases the overall result. Now let's see what this means in simple layman terms. Random forests build multiple decision trees and merges them together to get a more accurate and stable prediction. Each individual tree in the random forest spits out a class prediction, and the class with the most votes becomes our model's prediction. In the figure, 6 decision trees predict 1 and 1 predicts a 0. Hence, the final prediction of the classifier is 1. Now, the fundamental concept behind random forest is a simple but a powerful one: the wisdom of crowds. Now, what does that mean? A large number of relatively uncorrelated modules or decision trees operating as a committee will outperform any of the individual constituent models or individual decision trees. This is the most fundamental concept in random forests. The low correlation between models is the key. The reason for this wonderful effect is that the trees protect each other from the individual errors. While some trees may be wrong, many other trees will be right. So as a group of trees are able to move in the correct direction. Now let's see how the random forest algorithm works. First, create a bootstrapped dataset by randomly selecting a samples from the original data set. We can pick the same sample more than once. Then create a decision tree using the bootstrap dataset, but only use a random subset of columns in each step. Now go back to step 1 and repeat. Make a new bootstrap dataset and build a tree considering a subset of variables at each step. This results in a wide variety of trees. Now, the variety is what makes random forests more effective than individual decision trees. Now, how do we measure or ensure that the trees diversify each other? Bagging helps us here. Bootstrapping the data and using the aggregate to make a decision is known as bagging. Random forest takes advantage of this by allowing each individual tree to randomly sample from the dataset with replacement, resulting in different trees. Next is feature randomness. Each tree in a random forest can pick only from a random subset of features. In a normal decision tree, when it is time to split a node, we consider every possible feature and pick the one that produces the separation between the observation in the left node versus those in the right node. In contrast, each tree is a random forest can pick only from a random subset of features. This forces even more variation amongst the trees in the model and ultimately results in lower correlation across trees and more diversification. So, since we are selecting random features in multiple decision trees, they ensure that this will diversify all of the decision trees when combined together. Now, how do we implement this? For the implementation, we have two choices. We can either use the scikit-learn library to import the random forest model and use it directly, or we can write our own model from scratch. So in this video, we will implement random forest using the scikit-learn library. Let's start with defining a problem now. The task here is to predict whether a bank currency note is authentic or not based on four attributes, which are the variance of the image, wavelet transformed image, skewness, entropy, and kurtosis of the image. This is a binary classification problem, and we will use a random forest classifier to solve this problem. Now, for the dataset, you can download and learn more about the dataset from the link in the description. Let's start with importing the required libraries. Unlike my previous implementations where I import all the libraries at once, this time I'll import the library only when it is required. So initially we need NumPy and pandas library to handle the data. So let's start with that. Let's import pandas as pd and import NumPy as np and let that run and we're good to go. Now let's import the data set into our code. So data set equal to pandas.read csv is the name of the function and the name of the csv file is build authentication.csv, and I think I'm right here. Let me just check. Yes, awesome. Now let's get a high level view of the data set, and let's do that by executing the following command. So dataset.head, and as you know, we can see the first five rows of the data set, and you can see the variance, the skewness, kurtosis, entropy, and the class. Now here when you see the first five rows, you can see that the values in the data set are not very well scaled. So we will have to scale the data before training it. So to do all of that, let's divide the data set into x and y variables, which are the attributes and the labels. So x is going to be data set dot alloc to separate the values, and let's do 0 to 4 so that it's 0 to 3, and fourth is the class from 0 indexing, and we need the values, and let y be equal to dataset dot alloc, and we just need the last index, which is 4. So as these follow 0 indexing, we need the first 4 columns 0 to 3, which is variance, skewness, kurtosis, and entropy in the x variable, and the last column, the fourth column, class in the y variable. Okay. After this, let's divide the dataset into a train and test split. So for that, we'll need the train test split module from sklearn. So sklearn dot model selection, we import train test and split. Now let's have our variables ready. So let's train x test y train and y test, and let's give a function call here. So x and y, let the test size be 20%, so test size equal to 0.2, and we don't need a random state, so let's put that to 0. I think we're good to go. Let me just check back again, and yep, we have an error. So test size, it shouldn't be test, it should be test size. Sorry about that. Yeah, and we're good to go. So next, let's apply some feature scaling on our data so that the data can be really scaled and proper when we actually train it. So for that, we need something from the pre-processing module of sklearn. So sklearn dot pre-processing import standard scalar. Then let's scale both xtrain and xtest. So let's call the class first and make an object. So we have sc as the object, and now let's scale xtrain first. Sc dot fit transform xtrain, and x test is equal to sc dot fit transform x test. And now we have scaled the data set, we can train a random forest to solve this classification problem. Let's do that with the random forest classifier. So we can get that from the sklearn ensemble module. So ensemble. So since random forest is an ensemble of many decision trees, the ensemble module will contain the random forest classifier. Random forest classifier, and then let's make this ready, make the class ready. So let's say classifier is equal to random forest classifier, and first we need the n estimators, so the n decision trees. Let's say we have 20 of those, then a random state of 0 again, after which we are going to fit our classifier. So classifier dot fit x train comma y train, and let's actually save our predictions somewhere. So classifier dot predict x test. Awesome. And let's see what the errors are. So I think I have some uh, error here. So from sklearn dot random forest classifier cannot be named. So let me just see what the error is. Oh, I see it. There has to be a capital F. Sorry about that. And yep, we're good to go. Now the random forest classifier takes in n estimators as a parameter. The parameter defines the number of trees in a random forest, and we are using 20 trees here. So for classification problems, the metrics used to evaluate algorithms are accuracy, confusion matrix, precision, recall, and F1 values. Luckily, the scikit-learn library provides all these metrics out of the box. So let's actually use these metrics to see how good our model performed on this data set. So from sklearn dot metrics module, we're going to import a few things. So classification report is going to be the first thing. Confusion matrix is next, and we need the accuracy to see how good our model is. And let's just print all of them now. So confusion matrix is first, and y test, y pred, next is classification report. So classification report, again y test and y predicted, and the last is the accuracy score for the same parameters. And let's see how this works. And again we have some errors here, so let's solve them. Cannot import confusion, so you have to stop misspelling things, Ronak. Yes. So as you can see at the last print accuracy score, our accuracy is 98%, so that is good enough. And we can see the other metrics that are used for classification problems. So this was a very simple implementation of random forest with minimum data processing. Now, what you can do is practice more on Kaggle on a real life data set, which deals with more data processing, which can help you understand how a data scientist works. In this machine learning playlist, until now, we have only talked about supervised learning algorithms, where we knew what the output or the target variable was. In this video, we'll explore an unsupervised learning algorithm called k-means clustering. K-means clustering is one of the simplest and popular supervised algorithms, and there are plethora of real-world applications of k-means clustering, which we will talk about in this video. And in the next video, we will see the implementation of k-means and how easy it is when compared to algorithms like SVMs and etc. Now, before we jump into the algorithm itself or even supervised learning, we must understand what clustering means. So, clustering is the process of dividing the entire data into groups, or also known as clusters, based on the patterns in the data. Let's try to understand that with a simple example. A bank wants to give credit card offers to its customers. Currently, they look at the details of each customer and, based on this information, decide which offer should be given to which customer. Now, the bank can potentially have millions of customers, right? Does it make sense to look at all the details of each customer separately and then make a decision? Certainly not. It is a manual process and will take a huge amount of time. So, what can the bank do? One option is to segment its customers into different groups. For instance, the bank can group the customers based on their incomes. The groups that are shown here are known as clusters, and the process of creating these groups is known as clustering. Awesome. Now let's talk about unsupervised learning. Unsupervised learning is a type of machine learning algorithm used to draw inferences from datasets consisting of input data without labeled responses. So to understand all of this, let's see how a supervised algorithm works first. We have a labeled dataset with the output or target variable. In this particular example, the task is to predict whether a loan will be approved or not. As we have all the data labeled with appropriate targets, we call it as supervised learning. In clustering, we do not have a target to predict. We look at the data and try to club similar observations and form different groups. Hence, it is an unsupervised learning algorithm. So let's see where this helps us in the real world. So starting with customer segmentation, as we discussed before about the bank making clusters based on the income for the credit cards. Next thing is document clustering. This is another common application. Let's say you have multiple documents and you need to cluster similar documents together. Clustering helps us group these documents such that similar documents are in the same clusters. The next is image segmentation. We can also use clustering to perform image segmentation. Here, we try to club similar pixels in the image together. We can apply clustering to create these clusters having similar pixels in the same group. The next is recommendation engines. Let's say you want to watch or you want to recommend songs to your friends. You can look at the songs liked by that person and then use clustering to find similar songs and then finally recommend those songs to the person. So let's talk about k-means clustering now. We have finally arrived at the main part of the video. Now, with regards to generating clusters, our aim here is to minimize the distance between the points within a cluster. There is an algorithm that tries to minimize the distance of the points in a cluster with this centroid. This is called the k-means clustering technique. The main objective of the k-means algorithm is to minimize the sum of distances between the points and their respective cluster centroid. Let's see how the algorithm works in action. So we have these 8 points we want to apply k-means on to create clusters. So let's see how we can do that. The first step in k-means is to pick the number of clusters k. Next, we randomly select the centroid for each cluster. Let's say we have 2 clusters, so the k is equal to 2 here. We then randomly select the centroid. Step 3. Once we have initialized the centroid, we assign each point to the closest cluster centroid. Here you can see that the points which are closer to the red point are assigned to the red cluster, whereas the points which are closer to the green point are assigned to the green cluster. Now, once we have assigned all of the points to either clusters, the next step is to compute the centroids of newly formed clusters. Here, the red and green crosses are the new centroids. Now, we repeat steps 3 and 4. So, essentially, there are 3 ways to stop k-means clustering. First is the centroid of newly formed clusters do not change. So, if the centroids don't change, that means we have reached the end, and that is the best way we can actually cluster our data. Second, the points remain in the same cluster. So if the points remain in the same cluster, that means that there is no further possible way or a possible way to improve our clustering algorithm. And the last is the maximum number of iterations that are reached. So the number of iterations is subjective, so it depends from person to person. So we can actually focus more on the first 2 points and not on the last point as much. So coming to the implementation, we have 2 choices. We can either use the scikit-learn library and import the k-means model and use it directly, or we can write our own model from scratch. So writing our own model from scratch using NumPy and Python is very easy for k-means, but to see how the algorithm works very fastly, we'll implement k-means using the scikit-learn library. In this video, we will use scikit-learn to implement the k-means clustering algorithm. Let's get started. First, we import all the required libraries. So we need matplotlib dot pyplot as plt. We need numpy to handle the data, and we need the cluster from scikit-learn. Let's wait for it to run. The star here indicates that it's currently running and we have run it properly. Now let's prepare the data. Let's create a NumPy array of 10 rows and 2 columns. So it's better to actually show you how k-means is implemented using our own pre-made dataset and not a real-time dataset, because it gets really confusing. So we start with a simple handcraft dataset and then we move to a complicated real-life dataset. We create a NumPy array of data points because the scikit-learn library can work with NumPy array type data inputs without requiring any pre-processing. So we can directly focus on implementing the algorithm and not worry about pre-processing in the initial stages of implementation. So this is the NumPy array. Now let's visualize the data. The written code or the code which we're going to write, simply plots all the values in the first column of X array against all the values in the second column. So let's see what the code looks like. So we make a scatter plot and we start from 0 and we want Y values now, and let's give it a label as well while we're at it as true position. And this is how our data looks. So from the naked eye, we have to form 2 clusters of the above data points. We will probably make one cluster of 5 points on the bottom left and one cluster of 5 points on the top right. Let's see if our k-means clustering algorithm does the same or not. Okay, so let's create the clusters now. To create a k-means cluster with 2 clusters, simply type the following script. So k-means equal to the class k-means and number of clusters which we want is equal to 2. And let's fit the algorithm now to our data set X, and we've done that. And yes, it is just 2 lines of code to actually run the algorithm. In the first line, we create a k-means object and pass it to the value 2 as the number of clusters. Next, we simply have to call the fit method on k-means and pass the data that we want to cluster, which in this case is the X array that we created earlier. Now let's see what the centroid values the algorithm generated for the final clusters. So let's print them. And yep, those are our centroids or the centers. The output will be a 2D array of the shape 2 cross 2. To see the labels for data point, let's execute the following. So let's print k-means labels. So let's do it here again. So let's print k-means dot labels, and those are our 2 clusters. So it is point by point. So a cluster 0 and cluster 1. So the output is a one-dimensional array of 10 elements corresponding to the clusters assigned to our 10 data points. Here the first 5 points have been clustered together and the last 5 points have been clustered. Here 0 and 1 are merely used to represent the cluster IDs and have no mathematical significance towards each other. If there were 3 clusters, the third cluster would have been represented by the digit 2. Let's plot the data point again on the graph and visualize how the data has been clustered. This time we will plot the data along with their assigned label so that we can distinguish between the clusters. So let's write the code for that. We'll make a scatter plot again to see how this works with our data points in X, colon, comma 0 and X, colon, comma 1. And C is going to be k-means dot labels underscore, and let the C map be a rainbow. So let's see how that works. Here we are plotting the first column of the X array against the second column. However, in this case, we are also passing k-means labels as the value for the C parameter that corresponds to the labels. The CMap rainbow parameter is passed for choosing the color type for different data points. So that is how we get the differentiated bluish violet color or the purple color and the red color. As expected, the first 5 points on the bottom left have been clustered together, displayed with blue, while the remaining points on the top right have been clustered together with red. So here we have 2 different opposite scenarios. So the bottom has been done with red and the top right has been done with blue. Let's execute the k-means algorithm with 3 clusters and see the output graph. So let's implement it again. So k-means equal to k-means class, and now the clusters is equal to 3. Let's fit our data set on this algorithm and plot this again. So plt scatter X again, colon and 0, X with colon and 1. C is equal to k-means dot labels again, and the C map is going to be rainbow. And yeah, you can see that again the points are close to each other, have been clustered together. Now let's plot the points along with the centroid coordinates of each cluster to see how the centroid position affects clustering. So here we are going to also point out the centroids of all the clusters which we can see here. So we have 3 clusters here. So we'll be plotting the 3 centroids along with the clusters. Let's write the code for that. We always use scatter plot for k-means clustering because it's easier to see the scatter plot when we have to differentiate between the clusters. Colon and 0, and again 1. The C is k-means dot labels again, and the C map is equal to rainbow. Now we need to plot the centroids here. So let's try that. K-means dot cluster centers, if I'm right with that, and we need only till the 0th point, and we have to plot that with the y-axis. So cluster underscore centers underscore colon 1, and let the color of these points be black. Awesome. Let's see how this looks. So in the case of three clusters, the 2 points in the middle, which are displayed in red, have distance closer to the centroid in the middle, displayed in black between the two reds, as compared to the centroids on the bottom left or top right. However, if there were two clusters, there wouldn't have been a centroid in the center. Hence, the red points would have been clustered together with the bottom left or top right clusters. So that was a simple implementation of k-means clustering with our very own handmade dataset. Now you can go ahead and try implementing the algorithm on real world datasets. The k-nearest neighbors algorithm is a simple, easy to implement supervised machine learning algorithm that can be used to solve both classification and regression problems. Now, a supervised machine learning algorithm is one that relies on labeled input data to learn a function that produces an appropriate output when given a new unlabeled data. The KNN algorithm assumes that similar things exist in close proximity. In other words, similar things are near to each other. We can relate this definition to something like birds of a feather flock together. Now, notice in the image that most of the time similar data points are close to each other. The KNN algorithm hinges on this assumption being true enough for the algorithm to be useful. KNN captures the idea of similarity, sometimes called distance, proximity, or closeness, with some mathematics we might have learned in our childhood, calculating the distance between points on a graph. There are many ways to calculate distance, and one way might be preferable depending on the problem that we are trying to solve. However, we are going to use something called as the Euclidean distance, which is a popular and a familiar choice. Let's see how the KNN algorithm works in action. First, we load the dataset. Next, we initialize the number of neighbors which we want, which is k in our case. Now, for each example in our dataset, we'll calculate the distance between the query example and the current example from the data, the distance here being the Euclidean distance. Next, we add the distance and the index of the example to an ordered collection, for example, a dictionary. Now, sort the ordered collection of distances and indices from smallest to largest in ascending order by the distances. Now, let's pick the first k entries from the sorted collections, get the labels of the selected k entries. Now, if you want to find the mean, then that is the regression problem, and if you find the mode, it's a classification KNN algorithm. Now, let's talk about choosing the right value of k. To select the k that's right for your data, we run the KNN algorithm several times with different values of k and choose the k that reduces the number of errors we encounter while maintaining the algorithm's ability to accurately make predictions when given data it hasn't seen before. KNN has the following advantages. The algorithm is simple and easy to implement, and we'll see that in the next video. There's no need to build a model, tune some hyperparameters, or even make additional assumptions. It is a very simple and straightforward algorithm. The algorithm is also versatile. It can be used for classification, regression, and search as well. One of the major disadvantages of the algorithm is that it gets significantly slower as the number of examples or variables increase. Coming to this, let's talk about the applications of KNN. KNN can be useful in solving problems that have solutions that depend on identifying similar objects, right? The nearest neighbors or the nearest similar objects. An example of using this would be in recommender systems, which is an example application of KNN search. Now, at a large scale, this would look like recommending products on Amazon or articles on Medium, movies on Netflix. Although we can be certain that these companies, they all use more efficient means of making recommendations due to enormous volume of data. And when you have an enormous volume of data, that is when KNN starts to suffer. So that was a very brief introduction of how the k-nearest algorithm works. In this video, we will implement k-nearest neighbors using the scikit-learn library. So the k-nearest neighbors algorithm is a type of supervised machine learning algorithm. KNN is extremely easy to implement in its most basic form and yet performs quite complex classification tasks. It is a non-parametric learning algorithm, which means that it does not assume anything about the underlying data. This is an extremely useful feature since most of the real world data doesn't really follow any theoretical assumptions, for example, linear scalability or uniform distribution. Let's start implementing the KNN algorithm using scikit-learn now. We are going to use the famous iris dataset for our KNN example. The dataset consists of four attributes: sepal width, sepal length, petal width, and petal length. These are the attributes of specific types of iris plant. The task is to predict the classes to which these plants belong. There are three classes in the dataset: Iris setosa, Iris versicolor, and Iris virginica. Let's start the implementation by importing some libraries. So we need to import numpy as np, import matplot lib.pyplot as plt, and import pandas as pd for data handling. Now let's import the dataset into a notebook and then into our pandas data frame. So here we have the URL from which we can access the data. The URL will also be in the description. We assign some names to the columns of a dataset and we read the dataset into the pandas data frame. To see what the dataset actually looks like, let's execute the following script: dataset.head, and we can see the first 5 rows of our dataset now. The next step is to split a dataset into its attributes and labels. To do so, let's write the following script. So x equal to dataset.alloc dot values, y is equal to the same thing, but instead of -1, it's going to be 4 because it's the last column. And let's fix this, and we are good. The x variable here contains the first 4 columns of the dataset or the attributes, while the y contains the labels. To avoid overfitting, we will divide a dataset into training and test splits, which gives us a better idea as to how our algorithm performed during the testing phase. This way, our algorithm is tested on unseen data as it would be in a production application. To create training and testing splits, let's execute the following script. So let's import the test train model from sklearn. And let's define some variables. So x test, y train, and y test is equal to test train split. That's a very big function name. X, y, and the test size is 0.2 or 20%. Let's wait for it to run so that we can see some. So test train split cannot be imported. Let's see what the error is. No, so it's train test split. My bad. That makes much more sense. I get it now. And we're good. So now the above script splits the dataset into 80% train data and 20% test data. This means that out of total 150 records, the training set will contain 120 records and the test set contains 30 of those records. Now, before making any actual predictions, it is always a good practice to scale the features so that all of them can be uniformly evaluated. The gradient descent algorithm, which is used in neural network training and other machine learning algorithms, also converges faster with normalized features. So let's write the script for normalization now. sklearn dot pre-processing import standard scalar, and the scalar is equal to an object, so standard scalar, and let's fit it now, not get, fit x underscore train, and let's x train is equal to scalar dot transform x train, and x underscore test is equal to scalar transform for test. And again, I think I made a mistake with the spellings. Pre-processing standard scalar. I'm sorry. Yes. Now let's fit the KNN algorithm to the dataset. It is extremely straightforward to train the KNN algorithm and especially makes prediction out of it when using the scikit-learn library. So let's import our model from scikit-learn. So sklearn dot neighbors, import k neighbors classifier, and let me just make sure that the spelling is right now so that we don't have any more errors. So k neighbors classifier, and the classifier is equal to, again, the same name of the class, and let's say we want 5 neighbors. Let's fit the classifier now. Again, fit not get for x train and y train. So the first step here was to import the KNN classifier class from the sklearn neighbors library. In the second line, we initialize the class with one parameter, that is the n neighbors. This is basically the value for the k. There is no ideal value for k and it is selected after testing and evaluation. However, to start out, 5 seems to be the most commonly used KNN algorithm. The final step is to make predictions on our test data. So ypred is equal to classifier dot predict for x test. Now let's evaluate the algorithm and see how good it performs. For evaluating an algorithm, confusion matrix, precision, recall, and F1 score are the most commonly used metrics. All of these can be found in the sklearn.metrics module. So from sklearn.metrics, import classification report confusion matrix, and let's print them now. So for y test and y predicted, and also print the confusion matrix to see the matrix. And the same parameters y test and y pred. And here we can see all the metrics which we need to evaluate our algorithm and how it performs. So this was a very basic implementation of k-nearest neighbors, and after this we can actually go on Kaggle and download a real life dataset and actually perform and see how Kanan performs on a real life data set. Thank you.